Welcome to all of my students. I will start lecture number 12. So we were discussing relations, equivalence relations in the last turn. Now see the definition. Let R be a relation on a set X then the intersection of all equivalences on X containing R is the smallest equivalence relation on X. Containing R. And it is called equivalence relation on X generated by R. And it is called equivalence relation generated by R and it is denoted by and is denoted by RE. Correct? Now next definition. Let R be a relation on a set X on set X then the relation R infinity, that is union 1 to infinity Rn, that is equal to R union R union R union R union R union R or so on is called transitive closure of R. Now we do lemma 1.4.8. Lemma 1.4.8 for every reflexive relation S on a set X, the relation S infinity is the smallest transitive relation, is the smallest transitive relation on X containing S, containing S. See what we have to prove. For every reflexive relation S on a set X, it is given that relation S is what reflexive relation, and we have to prove that this relation S infinity, as it is defined early in the definition, we have to prove that it is the smallest transitive relation on X containing S. It means that we have to prove two things. We have to prove that it is transitive relation as well as it is the smallest transitive relation. To prove it is smallest, what we have to do? We have to consider another transitive relation, and then finally we show that this relation is contained in arbitrary transitive relation. So we start from here. So first we have to prove that S infinitive is transitive relation on X containing X. What is S infinity? See, S infinity, as we have already know, that it is by definition, that is it is from 1 to infinity, and from 1 to infinity is the union of Sn. And what it is given that S is reflexive. Given is that S is reflexive. S is reflexive. S is reflexive. That is equality. It contains equality relation. One X is contained in S. So we have to prove that it is transitive relation. So just take elements here. Take X comma Y. Take X comma Y and Y comma Z belonging to S infinity. So what is our claim? Our claim is that X comma Z belongs to S infinity. So when X comma Y belongs to S infinity, Y comma belongs to S infinity, it implies that there exists positive integer mn such that X comma Y belongs to Sm, S ki power m, and Y comma Z belongs to S ki power n. So X comma Y belongs to Sm, Y comma Z belongs to Sn. So it implies that X comma Y belongs to Sm composition S ki power m, as it's defined. This is the composition of two relations. S comma S ki power m is again relation, S ki power n is again relation. See, what is S ki power m? What is S ki power? S ki power m means S composition S. It is what? M times, like this. S ki power means S composition S n times. Correct? So now X comma Y goes in Sm composition n. What it is? Now S is composition of Sm times composition of Sn times. It means what? Of course it will be what? S ki power m plus n, and of course it will be contained in n from 1 to infinity and Sn, that is equal to S infinity. So we have shown that X comma Y, when X comma Y and Y comma Z belongs to S infinity, it implies it implies that X comma Z belongs to S infinity. It implies what? It implies that S infinity is transitive relation. Correct? Now what we have to prove? We have to prove this is the smallest transitive relation. To prove S infinity is the smallest transitive relation, we take another arbitrary transitive relation. Say you say sigma, and finally we show that S infinity is contained in that sigma. So let take another, let T be another transitive relation on X containing S, then S is contained in T, correct? It implies what? S composition S2 is equal to S2, S composition S is what? S2. So it means S composition S is contained in T composition T, and of course T is what? Transitive. So T is transitive, it means what? It will go in T. So S2 goes in T. Similarly, Sn minus 1 you can say that goes in T. So Sn can be written as like this, Sn minus 1 composition S. It means it goes in T, composition T, it again goes in T. So it implies that S infinity goes in T, Sn goes in T. And so finally we can say that this n is greater than or equal to 1. So of course S infinity goes in T. So in this way we have shown that hence S infinity is the smallest transitive relation. So in this way we have proved of course before all we can just write also one thing that is clearly S is contained in S infinity. Obviously it's obvious, because S1 is of course contained in the union of all. So in this way we have proved that it is the smallest transitive relation containing S. Now we move to next result, proposition 1.4.9. So we will move to next result. Proposition 1.4.9. For every relation R on a set X, R E is equal to R union R inverse union 1x infinity. So we have to prove that RE is equal to R union R inverse union 1x infinity. So try to understand the problem. What is RE? RE is what? Smallest equivalence relation containing R. This is what RE is, what? Smallest equivalence relation containing R. So means what we have to prove that, for example, if it is, you assume that this is whole is equal to S. So it is equal to S infinity. So basically we have to prove that S infinity is the smallest equivalence relation containing R. Correct? So we have to prove that it is equivalence relation. First we have to prove that it is equivalence relation. And as in the previous lemma, we have already proved that S infinity, where S is any relation, isn't it? S is any relation containing R. We have already proved that. See, in the previous lemma, what we have proved. This is what we have proved, that it is. In previous lemma, we have proved that is R infinity is the smallest transitive relation containing R. So we have already proved. It means by previous lemma, what we have? We have S infinity is transitive relation, smallest transitive relation containing S, and of course S also contains R, because S is equal to R union R inverse union S. So S infinity is the smallest transitive relation containing R also, because as R is contained in S. S is equal to what? R union R inverse union 1x, correct? So what we have to prove, in order to prove S infinity is equivalence relation, what we have to prove? It is transitive by previous lemma. We have to prove it is reflexive as well as symmetric. So it is very easy that it is reflexive also. Why? You see that first we will show that 1x is contained in, of course, R union R inverse union 1x, that is S, and of course it is contained in S infinity. So 1x is contained in S, and this is equal to S, and the S is contained in S infinity. So 1x is contained in S infinity. It implies that S infinity is reflexive relation. Correct? Now we show that S infinity is symmetric. So before proving S infinity is symmetric, first we show that S is symmetric. Let x comma y belonging to S, that is R union R inverse union 1x. It implies that x comma y belongs to R, or x comma y belongs to R converse, or x comma y belongs to Ix, means x is equal to y. Correct? So it implies that y comma x belongs to R converse, or y comma x belongs to R converse. Converse is R, of course, or y is equal to x. So it implies that y comma x belongs to R union R converse union 1x, and of course it is equal to x. Also we can go reverse. So it means that x comma y belonging to S implies y comma s belongs to S. Correct? So it means what? It implies that S is equal to S. So x comma y belonging to S, y comma x belongs to S. It implies that x comma y belonging to S converse. So it implies that, so S is equal to S inverse. So it implies that S is what? Symmetric. Symmetric relation. Correct? Because y comma x belongs to S, so x comma y belongs to S converse. So we have taken x comma y in S and we have shown that x comma y is in S converse. And also if x comma y is in S converse, then x comma y belongs to S. So S is symmetric relation. Now S ki power n we can write like this, S inverse ki power n, because S is what? Since S is equal to S converse. Now it could, we can, this is equal to what? Sn, we can write like this, Sn converse. So it implies what? Sn is symmetric. Sn is symmetric. So we have proved that S ki power n is symmetric, because S ki power n is equal to S ki power n converse. Both are equal to each other. Sn is equal to Sn converse, both are equal. It means what? This is the relation, assume that it is rho. So rho is equal to rho converse. It means what? Rho is symmetric. When rho is equal to rho converse, it implies that rho is symmetric. So Sn is symmetric. So Sn is symmetric. Now you see that what is S infinity? S infinity is what? Union of 1 to infinity Sn. So union of symmetric relation is, this is the fact, all of you can verify by yourself. Union of, arbitrary union of, yeah, you can see, first you can see the two union of symmetric relation is again symmetric, and also arbitrary union of symmetric relation is again symmetric. So you can write Sn, S infinity union 1 to infinity Sn being union of symmetric relation is again symmetric. Correct? So S infinity being union of symmetric relation is again symmetric. So we have proved that S infinity is symmetric as well as reflexive and transitive by previous lemma. So S infinity is what now? Equivalence relation.